I would like to introduce Model Error Compensator MEC in this video. The proposed control system structure adds robustness for existing control systems. URL of corresponding journal papers are in the text box. This is the structure of MEC, and the compensated system is used in the existing control system like this. Then, MEC minimize effect of model uncertainty and disturbance appropriately. Details of the MEC is explained after this slide. First, I would like to introduce background of the model error compensator. Most of the control systems are designed based on the plant model. Model-based control is widely used for control systems design. Examples are like these. It is easy to design controller for various types of plants using existing methods. This slide shows the order of designing controller. At first, mathematical model of actual plant is derived by using system identification. Then, the controller is designed using an existing model-based design method. This designed controller is applied for the actual plant. Then the desired output is achieved for the control system. However, intended output cannot be achieved when the model mismatching or model error exists. Therefore, the existing model-based design methods are very useful, but there has a demerit. It is difficult to overcome model uncertainty and disturbance. The bottom figure shows the transience response for various parameter uncertainty. Transience response are fluctuating by error between the model and the plant. To overcome this uncertainty, robust control is developed. Controller is designed for a set of models in the robust control. Then the high robustness is achieved. This is a traditional robust control concept. Set of differential equations are considered as a model set. Then the controller are designed for a set of models. Designed controller act to achieve good performance for all models in the set. However, traditional robust control concept includes some demerits. Because problem formulation becomes complex and includes some assumptions, the conservative results are obtained. In conclusion, improving the robustness of standard model-based control is considered useful. In our research, we attempt to add robustness for standard model-based control. In our approach, we add robustness for existing model-based systems using compensator like this. Upper figure shows the standard robust control. The lower figure shows the control structure of the proposed method. We can find that the lower figure includes controller which is designed by existing methods. The plant is represented by symbol P. The plant consists of nominal model and model uncertainty. In case model uncertainty is 0, desired feed-forward control is achieved by this block diagram, where TD is desired input-output. On the other hand, there exists performance degradation caused by model uncertainty if delta y not equals 0. To overcome this problem, we add modular compensator like this. H is desired to minimize model set of P dash. Desired function of compensator H is written as follows. First, P dash is stable if P is stable. Second, in case delta P is 0, then P dash equals to Pn is satisfied. Third, filter H is designed to minimize the effect of delta P. The system structure of proposed MEC is given by this figure. Filter H include model Pn and feedback controller CFB. Filter CFB compensates the effect of delta P. We can see that the MEC is simple structure. Because Pn is given, we have to design filter CFB, which works well for model uncertainty. In other words, filter CFB enforced to minimize effect of delta P. To satisfy desired function of H, it is required to satisfy the feedback loop L is stable. The robust stability condition for the case of SISO system is written by the following inequalities. We can find that this formulation is very simple. To evaluate control performance of MEC, we consider this block diagram. Weight function WE and P dash and Pn are used. In this diagram, we want to minimize the error between y and yn. The transfer function from u to the error between y and yn can be given by this equation. We can control red frame part by, in the red frame part, small gain is better. In this framework, high gain feedback is one approach to minimize the red frame part. This slide shows the design problem of CFE. Design problem can be solved numerically by standard mu synthesis problem. This slide shows the numerical example of MEC. Left figure shows the feed-forward control and right figure shows the feed-forward control with MEC. We can find that the robustness is increasing by adding MEC. We can use MEC for many control systems. This slide shows a feed-forward system with MEC. This slide shows a state feedback with MEC. This slide shows unit feedback with MEC. These figures show example of MEC. Also, we can use modular compensator for many control systems, like MPC. At the last of this video, we show an example of robust control. Robust path following is considered in this slide. In the vehicle control, mass M and I depends on number of human and luggage. Moreover, cornering power coefficient depends on road condition. For example, K is small in rainy road. This structure shows the path following control with MEC. This control system includes path following controller and vehicle model. These figures show the path following control at Rainy Road. Left figure is the traditional path following control and right figure shows the proposed method. Dashed line is desired path and solid line is vehicle trajectory. Vehicle start at the bottom and running counterclockwise. We can find that the right figure is better than the left figure. So the robustness is increasing by MEC. We start this research from 2011. Please click here for PDF files. This concludes the video introduction to the model error compensator. Thank you very much.